Hey, welcome back. I just took a look at all of our work on the Getting Started project. So I'm just checking in here, making sure video and audio is okay. I just took a look at all of our work on, all right, seems like we got video, we got some audio, looking good. And I wanted to walk through some of the work that I saw and like some places where we can maybe answer a few questions or dive a little bit deeper based on the work that I saw. So most people had no trouble kind of getting to like some measure of k, whether you used a forward difference or a backward difference. There was one interesting thing that I saw that instead of using this t sub t, there was another one that was t sub the average of the two. So 85 plus 80 over 2, and where it ends up being like halfway between. So you, instead of saying that it's either the first temperature or the last temperature, end up there. But no matter what we use, they're all kind of the same thing, right? All right, so we need this one. I need to do that, and I need to do this. I'm just grabbing, and what I'm gonna do is copy this in there, because this is kind of a neat way of doing actually, let's do that. So one thing, some people tried this, other people didn't. I saw there are some people are still using this like input of something, like give me a number, and I'm trying to get myself, there we go, calc K. So some people are still using that input thing. This is something that I really don't like to add in my, if I'm trying to do computational work. It's fine if you're like designing some kind of like user interface, and I guess even if you were going to design like a user interface, you wouldn't want to use like an input. You'd want to use some kind of like let's see what the options are for Python GUI. TK enter is one. So you can get like buttons, PyQt, TTK bootstrap. But there's just better ways. This function here that's called input is kind of the old method of like how do you get a user to stop the program, interact with, change what it's going to do, and then do something else. So I don't particularly like it. There's just better ways to interact with Python programs, and we're already creating like a script. Oh, this thing is still waiting on me. Yeah, so there I get like K is 0.38, which is exactly what I got here, so I'll use that one. You can use a different K if you want, but the main thing that I wanted to do was get into this third part of the problem where we have an analytical solution. So this one, it doesn't matter how many time steps I use for this. So let's try that out. I'll say t analytical is, and this one's kind of a fancy function. Lambda t is going to be ta, or wait, what do I call it up here? T ambient, T final, T initial. So T ambient plus T initial minus T ambient times np.exp of negative k times T. So if I ask for T analytical at time 0, well, if I actually import the libraries that I need to use, I'm going to go to the top, run this first one, and then go through and run the rest of them. At time 0, it's always going to be 85. At 10 hours, it will always be 65.4. It doesn't matter if I ask for 9.999 and then 10 or 9 and then 10. So let's define my time from 0 to, let's do like 5 hours. And put it as squares. Oh yeah, I should say t of t. So this is my analytical curve. I put it all as squares so I can see where the dots are. So right now there are 50 time steps between 0 and 5. But if I change that to 100, it's the exact same curve, it's just more dots. And to show you that it's definitely the same curve, if I can plot it once, I can plot it as many times as I want for n in bracket 50, 100, 200. No matter what I do, it's always like every one of these dots are directly on top of each other. There is no difference between any of these lines. They're all exactly the same. And that makes sense because a function is a function. Like, it just doesn't change. And this is the solution to this differential equation. So if we can make a numerical method that can get to this line, then we can make a numerical method that can get to any line, even if we don't know what that line really is. So that's what we're trying to show here, is like, can we get the Euler method, the Euler integration, to converge to this line? There's different ways of showing convergence. We looked at, in homework 1, we took a look at like this, looking at convergence of this truncation error. It's the same problem with this, oh my god, with this heat transfer problem. And then we also talked about it a little bit. We had the question of like, okay, if I decrease the time step or increase the number of evaluations in this population growth model, what happens? And the answer is that it should go to that e to the kg times t function. That's what we're trying to show. And again, there's more than one way to do that, but here's one or two ways that we can try that. So I have my analytical solution. I have linspace, and for now, let's get rid of, well, let's just take that out of the for loop, and I'm gonna get rid of this for loop for now. And let's stick to maybe 11 steps, or yeah, 11 steps, that's fine. Oh, and this is something that came up a few times. People were we're trying to define like time steps like dt and the max time. The way I like to do it is always use linspace, because then I can define my start, my stop, and the number of steps. And now I can say dt is t1 minus t0. And this is a nice like two-step with these kind of 3 lines. I can say how many steps do I want, how far do I want to go into the future, and then now my time step is based on those two. But I saw like a few different things. If you like, so if I want to go through and say dt is half an hour, then a range is really kind of supposed to work. Like 0, 5 and that time step, but sometimes you end up with, so in this case it goes 0 to 4.5, so I can say like plus dt, and now it goes to 5. But I think there are sometimes, yeah, like in this case when I say go to 5.6, I want to do 0.6 hours, not for any particular reason, but when I ask it to go to 5.6, it doesn't get there. Well, when I ask it to go to 5, sorry, when I ask it to go to 5 hours, it doesn't get to 5 hours because dt, I can't add dt and make it 5. So a range, it works well, but sometimes it's better. I'm trying to think of how to do this. The main thing that a range is meant to do is it's meant to have like integer values. So like 0 to 100 with steps of 10. Like that's a good a range, or steps of 5, something like that. Those are good for a range. Linspace is much better for cases of like I want to go 0 to 5 and take a number of steps. So we'll do 11 steps. And now it gives me 0 to, every time I ask for a 0 and 5, it keeps those numbers as part of my step size. So anyway, take that with a grain of salt. I like linspace better. If you don't like it, you don't have to use it, but it works really well for this kind of approach. And then my dt is just that t1 minus t0, so it's going to be 1/2. Okay, so that sets up, and again, time is an independent variable. We call it independent because we get to choose where we want to evaluate the time. Like I could have said 0 to 100. I could say 0 to -100. I can take time and go any direction I want with it. Now we get to the dependent variables. So so that was my analytical solution, but what I'm trying to deal with is this differential equation. So let's set up my variables. This is called initializing. So I'm going to create a vector that for every point in time, it has a 0. And then I'm going to go through and rewrite all those zeros as the actual numbers that I'm trying to calculate. So the first number that I know that I have is that first 0, and that is my t initial. All right, cool. So step 1, I solved 1 out of 11 times. So now I just need to figure out the next 10 temperatures. And I'm going to do that inside of a for loop. I guess I could do it line by line, right? I could say T Euler of 1 is T Euler of 0 plus the change in the temperature, which is going to be that negative K, is it capital K? Capital K times T Euler 0 minus T ambient times that dt. And that would tell me, so now I've solved like 2 out of those 11 temperatures because I knew the first temperature. Now I'll solve for the second temperature. So then I could take this and I could plug it in down here. I'll do my magic cursor. Change those all to 1. Change that one to a 2. Now it goes 85, 81, 78. But we can see the pattern. We're just copying and pasting. Everything after this first one is the same thing happening over and over. So rather than copy pasting this over and over, let's delete it, put this inside of a for loop. We'll start at 1 because that's this first value that I'm doing. Go to the length of t, and this one's going to say I. This one's going to be I minus 1, and that'll be I minus 1, just like that. And then I still go with those same first 3 values, but it fills in the rest of my values here. Okay, so now I can say plt.plot t comma t Euler, and now I want to make that one squares, and I want this one to be a line. And what I see here, and actually there's a nice, do I want to say that? We could do that. So someone printed out a table of all of these results. So /t dot format of t bracket I, t Euler bracket I, and t an of t bracket I. So 0 at time 0, they have to be the same temperature because they're both starting at the same temperature. Then at half an hour, there's an error of 0.3. Then at 1 hour, there's an error of 0.5. And by the time I get out to 5 hours, now the error still about 0.55, but it seems to be growing, right? And I could take these two and subtract them if I want to look at the error. /t. Wait, I want to do 2 t's here, like that. That first line is just messing me up. That's okay though. So I can see the error starts at 0.3 and goes up to 0.6. So it starts dropping again. I mean, it'll start dropping as we get towards like steady state, because whether or not I'm converged to the right solution, it's gonna go towards 65 degrees. Okay, so I just wanted to print out that table a little bit just so we could take a look at it. But we're not really showing, so in this case, the reason I wanted to show this table is like this doesn't really show that the answer is getting better, that I've converged to a solution. And even looking at this graph, it's a different value. And it's like, well, okay, well let's make it 10 times bigger. And now, yeah, that's a whole bunch of nonsense, so we don't need that. And now, yeah, it's getting closer, but is it the same? Like, isn't there still error here? So, and the fact that I used 11 and 101, is it getting closer and closer to the answer? That's the thing that we're trying to figure out right now. So one way that we did it that you can look at it in the reading is we were looking at like free fall examples, and I think, let's see, let's just do a kernel restart run all. So in this case, we looked at like what was the sum of the errors, and we can see that it keeps dropping. Then at some point we hit like truncate. We start hitting round off error in this case. You don't have to go through and show like this log plot for what the error was in this, but some kind of evidence there. But if I wanted to do that, one thing that I saw from that, here, if we go back to 11 steps and I uncomment this, I can see that the longer time goes, I mean, here it's kind of like 3 hours is my max, like error here. So I could change this to like 3, and again the numbers start jumping. Like I need better formatting in my table output, but for the most part about 3 hours, that's where I'm seeing like the max error here. So I could just take that value, I could go from 0 to 3 and then see what the difference is. So print t Euler bracket -1 minus t an of t bracket -1. And the error there is 0.43. And if I make it 101, now it went to 0.04. So 10 times more time steps, 10 times less error. If I go to 1001, now it's 10 times again, 10 times less error. It keeps getting closer and closer. So instead of just like printing this result, I'll say error bracket n equals that. And if I'm creating this error n, then I need, so how many do I have? 1, 2, 3, 4. Actually, let's do this. Same thing, just initializing that vector. And then I have to say for n in capital N. And, oh, and I have to change that to a little n. And now index 11 is out of bounds. Okay. All right. So then let's just do this. Error is going to be an empty list, and we'll say error dot append that guy. And just like we saw in the homework for this exponential Taylor series, it looks like it quickly drops to 0. We only have 4 data points here. I could add as many as I want. We could even add, we could make like 5 over here. Like it looks strange. So let's look at log, and we want to do absolute value of the error, because we don't really care. And now I can see that the more time steps I have, the smaller that error is getting. So this is one way of, this is like the actual definition of like what is the convergence of this method, of this numerical method. And it's showing like, okay, the more time steps you have, like on a scale of, on a log scale, the smaller that error becomes. And you could say like what is this? Or you could say like 3 over n, because that's like, oh my god, np dot array of n. So this would be like time steps, how many time steps there are. And I think it would be +1, n plus 1, or n minus 1. But that's all right. It's on a log scale anyway, so if I add or subtract 1, it'll basically be the same graph. But big time steps, big error. Small time steps, very little error. Lots of time steps, and they're inversely proportional. Okay, so that's one way of showing, like demonstrating what is the convergence of this plot, or of this method. The other way is saying like, all right, well, if it keeps getting closer, if the graphs get closer to each other, and I can see that there's demonstrated as this n goes from 5 to 11 to 101 to 10,001, it gets to be a better graph. That's another way that we could show that it is getting closer. So right now I have like a single set of squares here, but I could add we'll just say dt, and those are hours. Oh yeah, I have to put that f at the beginning, right? So for 3/4 hour, and oh yeah, I like, so my preference for this is that if it's an equation, a continuous equation, leave it as a line. But meanwhile, for like discrete points, because this Euler method is not actually creating a function, it's just calculating discrete points on the graph. Oh, and don't forget your commas. Now I can see blue dots are the farthest away, red dots are a little bit closer, green dots are, I can't even see them, but then these gray dots, when I get down to like 0.0003 hours, there's no difference between this purple line and those gray dots. And this should probably have a label, right? analytical solution. So by the time I get to that purple line, like these gray dots, they're exactly what that analytical solution is. All right. And maybe that seems like a lot of work, but the nice part is that it's always the same process. Whether or not I have this purple line, I can keep decreasing those time steps and show that, look, as dt keeps decreasing, it does not change. There's always this one line that it's always getting to. And even on this plot, it would be the same plot on this. The only difference is instead of having like an absolute value here, we could look at a relative error of like, based on the previous Euler solution, what was the change in that final temperature calculated. So it's always, numerical methods are great because it's always the same method. You always process it the same way. All right, so now I've got two methods that both produce the same equation. And I can start answering these questions about like, all right, what's the final temperature? If time goes to infinity, what's happening? One way I can do that, since both of them are the same, both of them create the same temperatures at the same times, is I can solve for what value of time ends up with t analytical, or as this t goes to infinity, what does t analytical become? And in this case, taking the limit, I can say e to the negative k times infinity is 0, and then I end up with t analytical is ambient. Or I can plug it in, right? T analytical of 10 hours, pretty close to 65. 100 hours, it is 65. And let's do a print. Where did I mess up there? Oh, one more parentheses. And colon 1.20f and 40f. All right, so it looks like it's 65. Even at 50, it rounds to 65. So we quickly eat, and after 100 hours, it's basic for this time constant. 100 hours is infinite time. And so that's one way to do it. You could do the math out, like you could add your own markdown cell. Like, all right, so t right arrow infty. Oh, I don't need the slash there. But, and again, however you want to show that as t infinity, as you get to time infinity, then that temperature goes to 65. And then some people use the Euler method to find like when did this function reach 98.6. Other people plugged in this analytical, like, okay, at what time would 98.6 degrees happen? And since it's a function, you can invert the function, or you can, or you could kind of guess and check, which is what a lot of methods do. Like negative 1.5 hours, 100 degrees. Like, okay, well then it's less than that, 1.4. Okay, so it's still less than that. So let's go 1.36. And that's pretty close. 1.37. 98.64. Not bad, right? That's pretty close. There are better methods for guess and check, and we'll talk about them in Module 3. They're called root finding methods. But we can import them from scipy.optimize import fsolve. and then fsolve of t analytical, and give it some initial guess, -1. Oh, duh. lambda of t. So we're going to plug this in and say -98.6, like that. And the reason for that is that fsolve is always looking for, it's always looking for a 0. Like, when does that function equal 0? So I'm going to create, so inside here, I'm creating my own. Lambda is just another way of creating functions called anonymous functions, because they get used once and kind of thrown out. Or you can save them as variables, but it's so it needs an input of time, so time has to be the input, but when it gets to my answer, it has to be equal to 0. So now I get that -1.362 instead of 365. And I can even do that for Euler methods. So in this case, let's do this, because this is just like kind of a cool way, and we'll do this again in module 3. But in this case, so I want to say 1001, because I really didn't see a difference between 1001 and 10,001. So I'm going to have an input of this T Euler F that is a negative, so time of death in a negative direction. And now I think this dt, actually, let's do this, T death, but we'll add this here. So it's working its way backwards. And then the result that I want to return is the final temperature. So if I ask for -1.2 hours, it gives me 78. -1.3 hours, 77. Oh wait, sorry. So T death is working its way backwards. Negative time to so 1.3, and what we had seen before is that was pretty close to 98.6, and here I get 97.8. And now I could take this fsolve function again, and instead of T analytical, I'm going to say that it's my T Euler F, and I get the same value, 1.36218, 1.3618. They're a little different, like there's some truncation error still. I could make this even bigger, 1.36186, 183. So those are pretty darn close, right? Whether I use this Euler or that analytical to get the final time of death. Yeah, and then the next step is what is 11 a.m. minus 1.36 hours? So 36.36 hours is not 36 minutes, it's 0.36 times 0.36 times 60. 21.5 minutes. So an hour, 10 a.m., and then minus another 21 minutes. So it's like 9:39 a.m. Cool. Anyway, that's what I thought that this would be kind of interesting to like see another function, because again, the power of Python is not so much that you can write lots of Python code. It's more that you can import things that help you solve problems. So fsolve is great. As we get into module 3, we'll also try out some other like SciPy integration methods. So Euler is kind of the simplest and most error-prone method, but there's lots of better like Runge-Kutta and implicit methods that work for a bigger range of problems. All right, thanks for joining. Thanks for all the hard work, and we'll keep at it. Next up is module 2, doing a little bit of data science.